Hey everybody. I think for the first time I was able to achieve in context self-learning, as you can see in this chart, um, to solve difficult math problems. So the large language model actually learns over time to solve this difficult set of problems. They're actually currently running. Let's take a look. As you can see, it was able to improve itself. Actually, if you can see the very first in the beginning, it was just around 50%. So over time, it was able to improve by almost like about 15% over 500 durations. And it's still running. And I am also working on a tree search algorithm version of this, which actually achieves same level of performance much faster. But this is going to be another video because I need to still tune this. Actually, if I scroll, you can see the tree structure here that is being explored. Currently, this white spot is being explored. But anyway, this one is besides the point. This one was a sequential process which attempts to solve this problem, which is that this in this data set we have five numbers A, B from A to E, and they have a complex mathematical relationship. If you look at one of the solutions, you can see it looks something like this. So there is some mathematical relation between these five numbers, and then based on this mathematical relationship, they get categorized into one of four outputs or buckets. And the purpose of the system is to allow the large language model to explore this data set and actually create predictor functions such as these that actually accurately predicts the output, the categorization of each row. This particular solution, the 10th solution here by the tree search, actually here, for example, achieved 44%. So that's the idea. The Python file, which is the predictor generator, can either use OpenAI or OpenRouter. You can use any open router model, as a matter of fact. And we previously, let me just give a little bit of a background. When I did this previously, I've been working on this for a while now, if you've seen my previous videos. And before I continue, all the code files for this, except the tree search, will be available at my Patreon, by the way. If you're interested in downloading, exploring it, and modifying it, you can grab it from my Patreon. The link for that will be in the description and in the comment, depending on where you're watching this from. Anyway, when we tried this previously, and I've been going at it for a while, the maximum accuracy we could achieve was 0.472%. And not only that, but if we look at the accuracy progress, we saw that it was pretty flat because we want accuracy to increase and improve. As a matter of fact, I have graphed the all models accuracy, which we looked at in the last video or the previous video. This black line in the middle is the average of all the training runs that I've done, like literally dozens of them. And essentially, it's flat. Sometimes it feels like it's going up a little bit, but at the end, actually, it actually collapses a little bit. And if you look, we are just around 40%. Now, the random choice of like if somebody were to choose randomly, we would be at 25% because we have four choices. So the models actually learn something about this problem, but the purpose of my experimentation with this is to be able to allow a model to learn over time. And we didn't see any evidence of this, but with this, I can now say for sure that this was the first time I've seen evidence that that a large language model can actually learn over time. And I will tell you the difference, the thing that made the difference. Although towards the end it collapsed again, I keep running it. So this has been running for over 12 hours, but we can clearly see the progression, almost a 15% jump over about 600 iterations. So the and here's another view of the tree structure. That's for another video. So previously, we were making separate API calls for each iteration, but we were learning something from this API call. We were distilling it, whether in natural language or in code, and then we were crafting some kind of prompt with some examples from the data set, like what worked, what didn't work, or natural explanations, predictive explanations, which we got from the one call and pass it to the next call. And we were doing it like this, right? Going across like this, and these results were achieved like that. And obviously they're pretty flat. So I was disappointed by that. And I have actually tried a different attempt where I again ran into flatness. And this was a similar idea, but this was starting from an origin point and exploring many different alternatives before combining it into one solution. And this again resulted in a flat trajectory and did not really result in the model learning anything, or at least from the indication of this graph. However, with the new idea that I had was to actually allow the message history of a single message history to accumulate all this information. So rather than engineering a special prompt to pass on to the next API call where we clear the message history each time, I thought in the same way, well, let's make a call, let model learn something, but then it is still the same model that is going forward. So the message history is actually continually growing. But when I did this at first, these are the results. These are the old results from the old script. So I've run it across multiple models, but here is, for example, the chart for Sky, running it at 200 iterations. I clearly saw that the model actually learned something pretty quickly, just above 60%, but then flattens out and does not improve. So this is GPT OSS. Again, it improves and then flattens out. This is below 60%. This is next one is GLM 4.5. Again, it learns something, it flattens out, even dips. This dipping at the end almost always happens for some reason. It doesn't reach 60%, for example. So this was interesting, right? Uh, Here is also GPT-5. Again, pretty flat. GPT-5 Mini. So this is, but we do see this great increase in learning early in the iterations. So this was also a little bit disheartening to me. So therefore, I actually introduced cycles, as you see over here. So each one of these red dotted lines is actually a cycle where we let the model actually run. So we let the model run and produce solutions, and we calculate the accuracies of those Python solutions against the entire database, against the entire data set, which is quite large. It's actually 10,000. So we get each one of these Python solutions were tested against the entire 10,000 set of the data. So when you see this 58% accuracy, that's actually achieved via the entire data set. So this is way more robust. But anyway, so we allow the model to run one iteration. Maybe we give it like 10 row examples, and then let it run and create solution, and then apply that solution. Then we call that same model again, but with the same message history. Okay, and then this was the original idea, but at some point, like create a cycle and let the model when it reaches here. So this is maybe like 10 times. So we run this 10 times. So it's passing the solutions to the next iteration, and we pass at each iteration, we pass some of the rows that were answered incorrectly. But when it reaches the cycle 2, let's say C2, then it creates a reflective prompt. We can actually take a look. So it actually analyzes its progress so far. Let's take a look at it here. We can find it all the way at the bottom. So this is its last strategic reflection. So in cycle 81, so it analyzes what it has done and it creates a creative plan going into the next cycle. So there are some parameters here to control this. For example, we keep the top three best performers from all previous cycles, the top three performers, the script, the solutions, and also we keep the three strategic reflections. So these are all hyperparameters can be tuned. These are the numbers I just kind of randomly picked, but obviously there's some tuning to be done here. So we keep three of these reflections. So in this case, it will be 79, 80, and 81. And we pass it on to the next cycle and we clear its message history, except for a specialized prompt, which includes information such as, there's an example here, such as instructions, sample data, plus the best functions and where those best functions have failed. See, these are where the errors have happened. Also, the previous three reflections. So we pass those on to the next cycle, and then we repeat. So that go into the next cycles, the cycle three, and each time you see in the plot these little red or perforated lines, that means we are moving on to another cycle. Each cycle lasts for 10 iteration. That is determined by the parameter here, iterations per cycle 10. So that's another hyperparameter that needs to be optimized. The reason why I did this is because when you just let the message history to keep accumulating all this information like I did previously, which resulted in plots like this, previous plots, which was flat. Uh, uh, yeah, it was flat. So these cycles, even though we have cycles here, we did not have any reflective prompting. So I went through several stages. One, I was only using the full message history. Then went with cycles where we cleared the message history, and then the thing that made the most difference is actually the reflective prompt, which gave us this continual improvement, which reaches almost about 63, 64%, I would say, which is significantly higher than before. So this was the general idea, and then I had some discussion with GPT-5 here, trying to create a README but failing, and it also supposed that maybe we should give some of the hard examples, like some rows that are unsolved by any of the algorithms that were generated, any of the solutions. So if you look here, there's hundreds of solutions here. Is there any in the data set that none of them solves? So therefore, I created the script called find unsolved problems. When you run this, it actually runs very cool. It uses multiprocessing and whatnot. It generates this JSON file, which I would have to run again, I suppose. Interesting. This actually just happened. Look, my my prompt, both of my running processes failed, and now I'm actually getting a failure from cursor for Grok code as well. These were using Sonoma model, by the way. I should have said that in the beginning. So Sonoma Sky Alpha, very very good model in my opinion. Maybe there's something going on with XAI servers, but if you run this find unsolved problems, it actually looks very cool. Yeah, you can see it running. It's actually testing 734 predictor files under this folder on the entire data set. And it is going to create, if there are any rows in this 10,000 row data set that are unsolved by all of them. So unsolved by, so those are the ones that would survive this test. And then I have this, I made this slight modified version of the same script, which actually passes the hard examples to show, because GPT-5 recommended, look, show the hard examples which, could, maybe early on that maybe would result in better solutions. But it did not happen because here, we did find, so we only, in this case, we only found two rows that are unsold. But when I first ran it earlier, a few hours ago, there were 13. So I built this predictor generator with hard examples, but this didn't really change much. Here is the plot for it, and actually the hard problems were solved pretty quickly. So it didn't really impact. Maybe I didn't run it for so long, for only 100 iterations, but I didn't. If you when I looked at this in comparison to the chart, I didn't see any particular difference. Like if you look here at the 100, so they 100 iteration, they were performing just about the same. So I gave up that idea. But I went with the tree search, and the tree search definitely has promise. I'm actually kind of bummed that this crashed because I'd have to run this again. Anyway, there's some more improvements that I need to do to the tree search, such as it's actually running the children in parallel, but I also want to be able to run multiple branches in parallel. But I will make a separate video for the tree search. But in essence, the files here are predictor generator.py, the predictor evaluator, which is the evaluator function, and the API client, which makes a call either to OpenRouter and OpenAI API key. So these three are really what you need to run. This predictor generator with hard examples is just a additional experiment. This find unsolved problems is actually to go run the entire solution set against the data set and find if there are any rows that cannot be solved. So that's about it. Like I said, you can download the code files for this along with my charts and previous solutions at my Patreon. Link for that will be in the description and the comment. And while you're at my Patreon, take a look around. I have over, I think by now, 500 interesting applications that I built and shared, all related to large language models. If you'd like to become a member, you'll have access to them. And I also offer consulting services if you need help with your projects or want to learn something or just simply wanting to talk to me one on one. Take a look at that membership options as well. And if you do decide to become a regular member, then you will also have access to the weekly meetings that we have, the 1000x Lab meetings on Sundays. Well, thank you for watching and see you in the next one.